Hello again. So now we're going to talk about the mythical z-score. No, I'm just kidding. We're going to talk about the z-score, okay? I put the word mythical there to make it more exciting, okay? But the z-score is going to be very important for us, okay? First of all, what is a z-score? So for a probability distribution with mean mu and standard deviation sigma, the z-score of a particular value of that distribution, let's say x, is z, where z is given by the formula x minus mu over sigma, okay? And now, so notice that here when I said that, I didn't say it had to be a normal distribution, okay? And in fact, we can interpret it here, the first interpretation. It measures how many standard deviation from the distribution's mean a particular value is, right? So for example, okay, let's say I had a probability distribution, okay, with mean, let's say x is a random variable with mean, let's say 3 with standard deviation. Let's call that sigma to be 1. And I want to find and interpret the z-score of, let's say 4, like 4, for example. Okay? So how would I do this? So the z-score of 4 would be 4 minus mu, which is 3, over sigma, which is 1. Well, 4 minus 3 is 1. Divided by 1. I get 1 divided by 1. That's 1. What does that mean? That means that in the context of this example, where we have a probability distribution with mean 3 and sigma 1, if we want to find out what's the z-score of a value 4, let's say that x, this probability distribution, we perform the experiment, it pops out 4. What is that? What is the z-score of that value? The z-score of that value we saw here is 1, and the interpretation is that that value 4 is 1 standard deviation above the mean. If it had been a negative value, let's say it had been -1 instead, then we would have said that that value is 1 standard deviation less than the mean, or 1 standard deviation to the left of the mean. Okay? So now, I will say this though. Even though in this context, in the interpretation 1, and here, I have not stated that the normal distribution is necessary, this is almost always used almost exclusively with the normal distribution, okay? But you can interpret it this way, as being how many standard deviations you are from the mean, and that's like an important interpretation. And for example, one of the values of that is that, let's say that you want to compare like test results from 2 different classes. Let's say you have class A and class B. Let's say they're both taking calculus. They might have different means in their class, and they might have different standard deviations. One class might be very studious, the other class might not be so studious. And you want to interpret, like, let's say Sally got a certain value in class A, and Catherine got a certain value in class B. You want to find out which student performed better. Well, we can find out which one scored more standard deviations above the mean, because that would be a genuine measure of which student performed better. Okay, and I mean, I think you guys can see the picture there. But the reason why we're talking about the z-score now is because the z-score is incredibly important when we're talking about normal distributions, and it is for this reason. Okay. Now, by the way, I wrote this down carefully for us, so that it would be very carefully articulated. Okay. But I'm going to show you a visual image of what it means so that you guys can understand it on an intuitive basis, okay? But I do think it's important to write it down. Okay, so this is the interpretation that's important to us, okay? Given a normal random variable, let's call that random variable x. And let's say it has a normal distribution with mean mu and standard deviation sigma. And a particular value of that distribution, say x1, okay? The corresponding z-score, right, let's call that z1, where it's x1 minus mu over sigma. See, what I'm saying is that I'm taking a particular value of the distribution. In the case of my example over here, I'm talking about x1, right? And that's why I'm using this formula. And it has the property that the probability that the original distribution has a value that's less than that particular value x1 will be the same as the probability that the standard normal distribution will be less than the corresponding z-score. Okay? This is huge, okay? And the reason this is huge is because it lets us use a standard normal table to calculate the probabilities associated with any normal random variable, okay? So for example, visually, what this is saying is the following. If I have the normal distribution curve for my random variable x, which is normal with mean mu and standard deviation sigma. By the way, I know that you may see that this diagram is faulty, but your eyesight is actually fooling you. This is the most perfect normal curve you've ever seen in your entire life, okay? I want you guys to be aware of that. Okay, this is the location of my mean, okay? Okay. And then over here, I have my standard normal, which we're just going to denote as a z, okay? And it's the normal distribution with mean 0 and standard deviation 1. And so here, this is the mean, but here the mean is 0. We know that one offhand, right? Now, to make concrete what I'm saying over there, for any value of x1 I choose, let's say I pick x1 here, okay? Then the probability that the random variable x is less than that x1 corresponds to the area to the left of x1. So namely this shaded area, okay? Now in this case, because of the way I drew this picture, because the x1 is to the left of the mu, I know that the corresponding z1, okay, will be less than the mu also. So z1, which of course has the value x1 minus mu over sigma with this mu and this sigma, it'll be here. And the area, the probability that the standard normal, that the probability that an experiment that is modeled by the standard normal has a value that is less than z1 corresponds to this area, okay? And what this interpretation says, which is the interpretation we're using for the z-score, the interpretation we want to use here in the context of the normal distribution, is that the area, that if you take any normal random variable with mean mu and standard deviation sigma, if you take any particular value from that distribution and you calculate the z-score of that particular value from that original distribution, then the area to the left of x1 in that original distribution will be equal to the area to the left of the corresponding z-score in the standard normal, okay? And of course, as you guys will see me use in future examples, you know that this value here is exactly the value from the standard normal table, okay? Okay. And hence we'll be able to use it to solve problems. And so before I end this video, I just briefly want to tell you that even though I've stated this property in the context of areas to the left of a particular value, you will see as we work out some examples that this will basically preserve the properties, preserve the probabilities, whether we're looking for the probability that a particular value for random variable will lie within a range. Like in other words, a less than, for example, in this case, let's say the random variable is x, that a random variable will take on a value between a and b, and we know that that is given to us by this property, because if we have the upper limit b, we can get that area. The z-score the property we just had says that area can be calculated using this property, and then we can subtract the area to the left of the a, and that'll leave us with the area in between. When we see an example like that, you'll see what I'm talking about more clearly. And of course, the area to the right of the x1 in the original distribution will be equal to the area on the right of the z1 on this on the standard normal distribution, That one is easier to see, okay, because we can just see that if the area under the whole normal curve is 1. If you subtract this piece, you can see that that area is the same as that area because these areas match. Okay? Okay. But anyway, the most important part I want you to take away from this is the following. The z-score is x minus mu over sigma, where x is a particular value of a probability distribution, where that probability distribution has mean mu and standard deviation sigma. Now we can interpret it as the measure of how many standard deviations from the distribution's mean a particular value is. So in the context of this interpretation, we can use it to like compare values from different distributions to see like how far away they are from the mean, okay, and therefore assess comparative like performance, like let's say in the test example I gave. And finally, for us, and most importantly, the interpretation number 2, where the area to the left of x1 in any particular normal distribution with mean mu and sigma will be the same as the area to the left of the corresponding z-score z1 in the standard normal. This is the critical property we're going to exploit when we're solving our normal and variable problems using the z-score. Anyway, I hope you guys have enjoyed this, and I'll see you again soon. Thank you so much.